Hey guys, welcome back. So I'm re-recording the lab lecture for experiment 7 because I'm hearing that there are some problems with the audio. So I'm going to try and walk through this in a way where you can actually hear me. I think that might be useful. The way that I'm going to do this is to go ahead and share my screen and we'll talk about experiment 7. Now experiment 7 is 2 parts. The first part of this experiment, we talk about the activity series. In the second part, we talk about a redox titration, so oxidation reduction reaction titration. So in the first portion of this, we're going to be talking about the reaction between zinc and 4 solutions, H2SO4, CuSO4, Na2SO4, and AgNO3. And then we're going to swap out the metal and look at copper with all 4 of those same solutions. Now, while you have some data that talks about what happens with this, i.e. is there a reaction, not a reaction, the observations that were made, it's preferable to me to have you actually do this. Now, I don't care if you predict this or not. I mean, if you predict it, the idea is to say, okay, you think this is going to happen or not. Apologize, I'm having some problems with my internet. When that happens, but the idea is to have you look at, is this really going to happen, or is this actually not going to happen? I don't really care that you do the prediction. What I care about is that we actually do these and make the observations of these materials when we do this. Okay, so the way that we do that is to go into our D2L shell. Now I'm going to have you come into D2L and oh darn it, I need to close that. So we'll come into D2L, and in D2L, we'll go under content. Under exam 2, you'll find redox, and then you'll see oxidation reduction reactions experiment 7. So this is where we're going to need to be. Now this recording should be there. I'll have to fix that. We have our checklist for all the materials that are available for these, which include the lab manual, the data that's available, the summary, which we're looking at, and the post-lab. We'll walk through the summary and the post-lab in just a minute. The other things are this simulation for the activity series and the simulation for the voltaic cells. Both of those will be necessary to do this part of this experiment. So we're going to open both of those, both at the same time. Now, when we look at the activity series of metals, okay, this is going to encompass looking at CuSO4, Na2SO4, and AgNO3 with both zinc and copper. What we have here is that we have a metal and then an ion in solution. So for these first couple, you're going to want to set this metal to be your zinc. So zinc is your metal, and then you want your solution to be your Cu, copper, sodium, or silver. Now, notice that H2 is not here. We'll show you that in just a minute. But if we're going to look at, say, the copper one, we'll choose our copper. Notice that copper is Cooper, and that there's a couple typos. Gold is not capitalized the way that I think it should be. So here's what we're looking at for this one. Now, again, I don't really care if you thought it would happen. I'm going to say I thought it would happen because I think it will happen. So I'm going to say, yes, I think it'll happen. And then I'm going to say, okay, let's run this simulation. And so what you'll see over here is that the zinc gets replaced by the copper. So the copper comes in, becomes part of that metal, and the zinc ion atoms come out and become ions. So we've transferred electrons between the two, and we've got deposition of copper at that surface and zinc being dissolved. Okay, so I would say deposit copper, it colors that electrode, and then and so was a reaction observed? Yes, there was a reaction there. Okay, so if we look at some of the other things that might not happen, we could look at calcium. Let's see if that happens. See, and nothing happens there because even though the calcium comes and hits this surface, there's no replacement. Okay, so that's what we see when there's no reaction. Okay, so you'll need to do that for the zinc and the other solutions. You'll have this copper, sodium, silver, and you'll do the same for the when we have the copper metal here. You'll do the zinc, sodium, and silver. Okay, so that's one of those simulations. Now, the other one that we have to look at is this one. And what we see here is that we have zinc and copper, and there are electrons flowing in between them, all right? Now, the situation you want to set up is where you have zinc on one side and hydrogen on the other. So if we look for hydrogen, we can see that that's here. And we do see that something is happening, okay? What you want to see, what you need to see, is that electrons are flowing from the zinc metal to create Zn2+. That's what you're looking for. And that actually does occur. So bubbles appear because once those electrons leave the zinc, they travel through this and come over here to this side, and they react with the H plus that's in solution. And when we have two of those happen, then we make H2 gas, which then bubbles out. Okay, so that's the reaction that's happening. Now, what I'm going to show you is one of these other things, and I'm going to choose copper. And what I see here is that the electrons are flowing from this side to this side. So even though there is a reaction happening, it's not the reaction that we're looking for, okay? So copper is not becoming Cu2+. Cu2+ here is becoming copper. And so this reaction right here does not occur. This one is a yes, that one is a no. And that's because reverse reaction occurs. So there is a reaction, it's just not the one we want. Okay, so we don't see that here. Now, unlike the other simulation where we just didn't see anything happen. So that's what we need to talk about for that. So that's our simulations and what we need to do with this portion of the data collection. Now, when we talk about the rest of this, we're going to be looking at that titration that we're talking about here. So we have a titration trial, and this all comes from the information in the lab manual. So if I go to my lab manual and I scroll down a bit, I see the determination of mass percent of hydrogen peroxide. Okay. And it says to prepare the titration, we put our burette in there, we fill it with approximately 0.02 molar KMnO4. We need to see what the actual concentration is. And then I come and look at my data. In my data, it says the molarity of the KMnO4 is 0.198 molar. Okay, so it's not 0.02, it's 0.198. And that's, different than what it says in the lab manual, which it is. So we need to make sure that we're dealing with that when we talk about this. Okay. We're going to pour some of that into the burette. We set that up. Then we remove the funnel and record the initial and final volume. We'll talk about that in just a minute. In a small beaker, we put 10 milliliters of the hydrogen peroxide solution from the beaker into a 100 milliliter volumetric flask. So we put 10 mils and then to the 100. So we do a 10-to-1 dilution, 10 to 100 dilution of H2O2. Okay. And then we make some sulfuric acid. So we need to do this. So we need to make the 6 molar sulfuric acid because it needs to occur in acid solution. Okay. And then after the solution cools, we pipette 10 milliliters of the diluted hydrogen peroxide, what we made here. So we take 10 mils of that solution, and then we dilute that in the sulfuric acid solution. Okay, so we're going to take 10 mils of that original this diluted solution that we made, this one right here, and then put that into that beaker to be able to do this. So we start with 10 milliliters of this particular solution, the dilute solution that we worked with. Okay, we need to keep that in mind when we do our calculations. Now, it asks for some data in here, and it says volume of the diluted sample. So we use 10 milliliters of that diluted sample in both cases. All right. Then if I look at my data, what it says is that my initial burette volume in my first trial was 8.4 milliliters. And then my final volume is 28.1 milliliters. Move my mouse, you can see that. All right, it says to calculate these two down here, which we will. Okay, we're going to fill in our data for the second set as well. This is 4.6 is my initial, and then 24.7. All right. Now, how much of that solution I use is the difference between those two. So I take my 28.1, I subtract the 8.4. And that gives me 19.7 milliliters were used here. And then 24.7 minus 4.6, and that's 20.1 here. Okay. Now, it wants to know what's the mass percent of H2O2. And I go, okay, right. Well, I'm guessing there's information in the lab manual about that. So I'm going to go to my lab manual. And if I scroll up from the how I made that solution to this part that talks about doing this, there is a couple of pieces of information here that I need. One says that this is an unbalanced stoichiometric relationship between these two things. And then I need to use that to do this calculation right here. So I'm going to need to take the volume of MnO4 minus that we used in liters, multiply it by the molarity of the KMnO4, then multiply by the molar ratio between the H2O2 and the KMnO4, and then multiply by the mass of H2O2 per mole of H2O2. So there are a couple of things I have to find there. One, I need to know what that balanced equation is. So the first thing I'm going to do is balance that equation. Now, I'm going to need some space to do that. And I don't think I have enough space right here. So I'm going to say, okay, give me some space. I need some space. Here we go. Now, I start with MnO4 minus, and I know that that half reaction takes that to Mn2 plus. That's one of my half reactions. My second half reaction is the H2O2 going to O2. Okay, so those are the two that I need to be worried about. Now, there are some shortcuts we can take in this. I'm not going to talk about that a little bit in a couple of minutes, but I'm going to go ahead and balance this the way that we've been talking about so that we can get the practice of balancing this. So these are my half reactions. And of course, this one has one Mn on both sides. This has nothing except H and O, so it's okay. So that's my half reactions. Yay, awesome. The next thing I do is to balance O with H2O. Okay, now I have 4 oxygens on this side and none on this side. So I need to take my MnO4 minus to go to Mn2 plus 4 H2O. So that way I have 4 oxygens on both sides of that equation. When we talk about our H2O2 going to O2, I have the same number of oxygens on both sides. So yay, I don't have to do anything there. That's awesome. Now I can balance H with H plus. So I have 8 H's on this side, right? But I don't have any on the other side. So I'm going to add 8 H plus that MnO4 minus goes to that Mn2 plus 4 H2O. And when we talk about this one, I have H2O2 going to O2, and now I need to add 2 H plus to get the same number of hydrogens on both sides. Okay, so now I've dealt with my hydrogens. The next thing I deal with is the charge. And I balance that using the electrons. Now, my net charge, here I have 7 plus minus 1, and that gives me a total of 6 plus on this side. And I have a 2 plus on this side. Oh, sorry. I'd already done the math. This is 8 plus, and then 1 minus, which gives me 7 plus. So the difference is 5, and I have to add the electrons to the side that's more positive. So I'm going to have to add 5 E minus plus that 8H plus the MnO4 minus goes to Mn2 plus 4H2O. And if I look at my charge now, I have 5, 6 negative plus the 8 plus. That leaves me with 2 plus and then 2 plus over there. So I can see that I did that correctly. Okay, so that's that one. Now we need to add 2 electrons to this side because this side is neutral. So we need to add 2 electrons over here. So I have my H2O2 goes to O2 plus 2H plus 2E minus. And of course, now the charge on both sides is 0. Now, if I'm feeling a little weird and saying, I don't know if that's right, I'm not sure, I'm not sure, I can come to my exam handouts and I can scroll all the way down and I can see that MnO4 minus plus 8H plus 5 electrons goes to Mn2 plus 4H2O. So I know I balanced that one correctly. Now, I don't actually see the other half reaction in these, and that's fine. It's not always present. Okay, so we can't always use that trick to do this. But I do know that I have 2 hydrogens here, 2 hydrogens here, 2 oxygens here, 2 oxygens here, 0 net charge, 0 net charge. So I know that's balanced. Okay, so now I've balanced each half reaction, but I need to make sure the number of electrons is the same in the two of them before I can add them. So since I have 5 here and 2 here, lowest common denominator is 10. I multiply this by 5 and I multiply that by 2. That gives me 10 E minus plus 16 H plus 2 MnO4 minus goes to 2 Mn2 plus 8 H2O. Make sure you carry that 2 all the way through. And then we have 5 H2O2 goes to 5 O2 plus 10 H plus 10 E minus. Now, 10 electrons there, 10 electrons there, and they better cancel. One is a reactant, one is a product. They better cancel because that's what I was trying to do. We can cancel anything else that's the same. Now, typically we look at H plus and H2O. I don't have any H2O in this one, this second equation. So I can't cancel any H2Os. But I do have 10 H plus here and 16 H plus here. So I can cancel that. And that leaves me with 6. So rewriting all of that, 6 H plus 2 MnO4 minus plus 5 H2O2 2 Mn2 plus 8 H2O plus 5 O2. So we got to remember to get everything that's over here in there as well. Okay, so we haven't forgotten anything. I'm going to double check this because I am paranoid. So I'm going to look at H, O, and Mn. And of course, now I can't see what I have. I also need to look at charge. So if I scroll this back a little bit, I have 6 H's plus the 10 there. 5 times 2 is 10, so that's 16 total. I have 2 times the 4, that's 8, plus the 10 from here, that's 18. And then I have 2 MNs. And then if I need to look at charge, I have 6 minus 2, which is 4 plus. So 4 plus is my charge on that side. Okay. Now, H. 8 times 2 is 16. When we talk about our oxygen, I have 8 there. I have 10 there. That's 18 total. I have 2 MNs. And then when I look at my charge, the only charge I have is at 2 times the 2 plus, which is 4 plus. So, yay, everything's balanced. Awesome. So that is my balanced equation. Now, why did I balance that equation again? Because the lab manual says I needed it. Okay, so I need to know how many moles of H2O2 and how many moles of KMNO4. Well, the KMNO4 is the same as the MnO4 minus. So it's 2 moles of KMNO4. And then I have 5 moles of H2O2. So now I can start this calculation that I've got over here. So I need the volume of MnO4 minus that was used in liters. Well, I have a volume in milliliters that we calculated on this previous page, somewhere down here, 19.7 milliliters. Okay, 19.7 milliliters. I need to convert that to liters. So that gets me to liters. Okay, from the liters, then I'm supposed to multiply by the molarity, the moles per liter of the KMNO4. And remember, the molarity that I was given is that 0.198. 0.198 moles MnO4 per liter. The liters cancel, and that leaves me with moles of MnO4 or KMnO4 because it's a 1-to-1 between them. So I talk about them interchangeably. Sorry. We then know that there are 5 moles of H2O2 for 2 moles of KMnO4. So the moles of KMnO4 cancel, and that leaves me with moles of H2O2. But then I need to convert to grams, so I need a molecular weight for H2O2. Well, okay. Scroll back up, because I can't remember. So hydrogen is 1.008, 1.008 times 2. I'm going to add 2 times 15.999, which is the oxygen. And that gives me 34.014 grams of H2O2 per mole of H2O2. So moles of H2O2 cancel, and I'm left with grams of H2O2. So I do 19.7. Divide that by 1,000. Multiply that by 0.198. Multiply that by 5. Divide that by 2. And I multiply that by 34.014. Okay? And that gives me 0.331687.521 grams of H2O2. Now this number right here is 3 sig figs, so this answer should be 3 sig figs, 0.033, 0.332. 332. That's what we see. Okay. Hopefully that's not affecting this recording. While I'm trying to sort that out, I was trying to get to the mass of hydrogen peroxide in that solution, right? And I do that by dividing by the mass of the solution. Okay, so that's what it says in this thing over here. Is that I need the mass of the solution. Well, okay. So way back when we talked about this in terms of sorry. Here we go. So we took 10 milliliters of that solution, and we had done a dilution on it. So let's start with the mass of the solution that we use. Given that the density is 1 gram per milliliter, we're going to use that as 10 grams. grams. And since it's a percentage, we'll multiply by 100. So we divide that by 10 and then multiply by 100. And that gives me 3.316%. And actually should be 3.32%. So that's in that sample that I was talking about, that 10 grams that we were talking about there. Now, understand that that was a dilution 10-to-1, or 10 milliliters to 100 grams. So we need to multiply that by 10. Realistically, that tells us that initial solution was 33%. Okay. Now, I know that that's not really true. There is a mistake in this data that you were given. I understand that, but that's what that number comes out to be, and that's because of the mistake in the data that you were given. And I leave this because I need you to understand that if you make a mistake in recording something like this, you get funky numbers, and that's because there was a mistake. So this concentration, the molarity that's right here, should be 0.0. 3.198. And then we would get a 3% solution from our dilution. So 3.32%, if we multiply that by 10, that gives us 33.2% in the bottle. Okay, so again, I know that that's a mistake, but the data you were given says to do that. So since you don't know that that was a mistake, that's what you should do. I understand that that's weird. I get it. I know, but that's what we're looking at there. All right. Now, in terms of other things that we need to do for this, so the mass percent of the age, and I've only done one in the sample, is then 3.32. Yes. 2% and then 33.2%. Okay, so again, that is not correct, but that is the number that you're going to report. I'm going to leave you to do this calculation on your own to make sure that you know how to do that. Make sure that you can write down how we got to the balancing of that equation. Right? And I think that's everything for pre-lab. Yep, that's everything in pre-lab. So that's everything for the summary portion. Oh, that page is some anyway. So there is more. Where? Oh, sorry. Oh, that's right. Gotta go past this. There we go. So our objective is listed up here. So that is on page 46. This is from the last page. We did this, it was the very end of the last page. So right here. You're supposed to show that balancing. So that's where we're talking about. So it's the same balanced equation. Come on. So that's the one that we want to see there. Assuming the density of the diluted H2O2 is 1.00 grams per milliliter, calculate the mass of each aliquot used in the titration. Okay, so we took a 1.00 grams in each one, so we're talking 1.01. So we took that one, and we can do that. Using the stoichiometry and the balanced reaction above, calculate the mass of H2O2 in the dilute sample. Show all of your work. Place your answers in the data results table. Okay, so this is the calculation that we just talked about. All right, and then we do that for both trials. And the sample titrated was diluted by a factor of 10. So we multiply that by 10, and that's the one that we did, you know, the in the bottle calculation. And then the percent H2O2 on the bottle is 3%. Calculate the percent error for each of your trials. And this is going to be big. All right. So your percent error is given by your actual minus your theoretical over the theoretical times 100. My actual is the calculation I did. The theoretical is the 3%. Okay. So they're going to be big errors. Understand that that is the case. Are your results accurate, i.e., did they come out roughly the same? Approximately the same? Were they precise? Were they anywhere near what you expected them to be for that bottle? I would say no. But explain why. You need to explain why. And provide some source of error that affected your accuracy and precision. So were they accurate? Yeah, I would say that they're pretty close. You'll see that in the numbers that you get. Were they precise? No. What was the biggest source of error there? The lack of 0 that was in that number that was recorded. So instead of it being 0.0198, it was recorded as 0.198. Okay, and that is exactly what happened. why is it necessary to store H2O2 in a dark bottle? And related to factors that influence a chemical change. Now, I'm not going to answer this. Okay? There is some information in the lab manual about why this is true. There is some information online about why this is true. There is an answer out there. I really don't care what answer you give me. I want you to find something that makes sense to you. Okay, so that's our summary part. Now, we're going to close this out and we're going to talk about our post lab. It says, write the 4 net ionic equations observed in the electromotive series investigation. So when we talked about this, the data that we saw here, these reactions, there are 4 that are marked as actual reactions here. Those are the 4 that we need net ionic equations for. Now, one of them is sulfuric acid with zinc. Okay? So we have zinc solid plus 2H plus, gives me H2 gas plus Zn2 plus. And that is my net ionic equation. Okay, so you need something similar to that. You need to make sure that the number of electrons transferred is correct, all of that stuff. So you need to make sure that you've got those correct. You need to do this for the 4 X's marked in data. So those are the 4 we need to see. How many did you predict? I don't care how many you predicted. I just want to know, if you did the predictions, why were they right? Why were they wrong? Think about it. Now, if you didn't do it, that's up to you. But you need to understand why you made a mistake if you did. So that's where that comes from. Consider A, G, C, U, N, A, Z, N, and 8. Place them in a relative order of reactivity, most to least reactive. What we're talking about is this. So you'll see the most reactive is here, the least reactive is here. So you're being asked to rank those. Now, some of these are already on here. Now you're asked to rank SR, which is not noted in your list. And where might it fall? More or less related to Zn. So you get to make a guess about that. And you get to explain to me why you think that that's where it goes. Okay. So 4 of these are on this list. You need to say, okay, and they want them most reactive to least reactive. So whichever one comes first in this list, that's what you're going to say. Okay. Use the electromotive series to decide if a reaction would occur between each of the following combinations. Circle all that would occur. Now you can use this to determine if it's going to happen. I actually don't. I use my state of reduction potential too. And so what I would do if I were looking at this is say, okay, I want to find aluminum when it occurs in here, and I see Al3+. So we want to talk about the reverse reaction, the aluminum solid reacting with this thing. And so when we talk about reversing that reaction, we need to change the sign on this. And so I'm looking at Al solid going to Al3+ plus 3. E minus is 1.66. Okay. And then I want to talk about Ca2+. And I see Ca2+ is down here. And when we're talking about Ca2+, we got Ca2+ plus 2E minus goes to Ca solid. And of course, that is listed as negative 2.76 volts. And if I add those two together, I notice that that total is negative. Okay, since it's negative, that reaction would not occur. Okay, so you're looking for combinations that give you positive reduction potential. So make sure that you've got them in the correct direction, all of the rest of that. One of these 2 should occur, so I'm guessing it's going to be B that should occur, and one of these other 2 should occur. We want to talk about how many electrons are transferred in that process. Based on this, I see that there are going to need to be 3 there, but the zinc may be different, so you need to make sure that it's balanced when you talk about that. So this one, again, when we balance this, 3 times 2 is 6. It's going to be a 6 electron process when we talk about this. Okay, so you're probably going to see the same thing for this. Okay, and the same thing for the net ionic equation for these, how many electrons are transferred in that process. Okay, so make sure that you've got the same number of electrons in both of them. So if I were to write a net ion for this one, it'd be Al solid plus Ca. Hold on. We need to multiply this by 2 and that by 3. And that means I'd have 2 Al solid plus 3 Ca. 2 plus 2 Al 3 plus 3 Ca solid. Okay, so make sure that your number of electrons is the same. So that's what we're talking about there. Consider the titration reaction. Identify the oxidizing agent. Oxidizing agent. Well, okay, let's go back to our other to our summary, and let's look back here at our balance equations. So when we did our balancing over here, somewhere. So it asked me about reducing agent, oxidizing agent. So if we're going to do that, we got to talk about stuff. Now, my agents are always reactants. Okay. When we talk about our agents, we want to talk about who did what. Now, when I have this balanced equation right here, this is electrons are reactant. So this is gain electrons, reduce. This is my reduction. Here, lose electrons, oxidize because my electrons are here. This is an oxidation. And that means that this right here is my reducing agent. Since it is oxidized, it causes reduction in something else. It's an agent of reduction. The same is going to be true. This is an oxidizing agent. Okay. And so if we look at our post lab, it says the oxidizing agent is going to be the MnO4 minus. The reducing agent is my H2O2. Number of electrons that were exchanged is 10. That's my balanced equation for that, right? And that is the end of that post lab. Okay. So that should be everything that you need for all of that stuff. Sorry. So that should be everything that you need for all of that stuff. Now, I'm going to stop sharing my screen. Again, if you have any questions, comments, problems, please let me know. I will be happy to answer them in any way that I can. If we need to get on our WebEx, that's fine. And I will talk to you guys later. Thanks. Have a good day.